So welcome everyone for this new SIPTA seminar. So as you know, we do this seminar monthly now. Well, most of you know that we do this seminar monthly now, and that usually we welcome people that are connected to imprecise probabilities and to give general talks about it. So no, we are quite happy today to receive, to have the speaker, Frank Riedel, that will talks about imprecision and uncertainty in finance and economics. But in order to introduce him in more details and to chair the seminar, I will give the hand to Alexander that kindly agreed to chair this seminar. So Alexander, you're in.
Okay. So welcome everyone to today's SIPTA seminar. First of all, I would like to thank the organizers of the seminar for giving me the honor of introducing today's speaker, Frank Riedel, even though I'm only their second choice. And so perhaps I should briefly explain this. So the organizers first asked Max Nendel to introduce Frank, and for two very good reasons. The first being that he's attended the past to SIPTA, so probably known by several of you in the audience. And then the second reason is that Max Nendel and Frank Riedel both work at the Center for Mathematical Economics of Bielefeld University. Now, unfortunately, Max is unavailable today because he's somewhere on the road in South Africa. So since I recently visited the Center for Mathematical Economics, the organizers thought I would make a good replacement. And I sure hope that they don't regret their decision now. Anyway, so I must say that despite the horrible winter weather in Bielefeld, I very much enjoyed my visit to the Center for Mathematical Economics. And in large part, this is due to the very nice atmosphere that was there at the center. Now, from what I've seen and from what I've heard, Frank Riedel does a very excellent job as a director of this center. Now, that said, I must say, good that you know it. I must say that our interactions were limited to a couple of brief conversations at the coffee machine. Now, there can be several reasons for this, but I guess the main one is that during my visit, Frank was very much occupied with securing a ridiculous amount of funding from the German Research Foundation, and I can't blame him for having this prioritized. So what else do you need to know about Frank Riedel? Well, before landing at Bielefeld University, he got a degree in mathematics from Freiburg University and a PhD in economics from the Humboldt University in Berlin. Now, he then held a position at the same university, then decided to go on an American adventure that brought him to Berkeley and Stanford, after which he returned to Germany with an intermediate stop in Bonn before heading to Bielefeld, if I'm correct. Maybe he can correct this later. Now, the rest of his CV is very long, and I hope Frank doesn't mind that I'll spare you the details. But what I will say is that he's, from what I've heard, widely recognized as one of the leading researchers in the field of mathematical economics. Now, illustrative for this is that he serves as editor for two journals in this field and as editor-in-chief of the journal Mathematics and Financial Economics. And now this brings me to the topic of this seminar. So as you've just seen on the slide, Frank will be talking about Knightian uncertainty in finance and mathematics, in economics. Now, you may be inclined to think that this has nothing to do with imprecise probabilities, but I can assure you that soon you will realize that despite the differences in terminology, mathematical and finance and imprecise probabilities have quite a lot in common. Now, I hope you are excited as I am to learn more about mathematical finance and its connections to imprecise probabilities. So with that, Frank, the floor is yours.
Thank you very much for the kind introduction and for the opportunity to talk about my ideas here in this framework. I'm going to need a second now to share the screen. Let me do this. Yeah, no, it has been a pleasure, actually, Alexander, to have you with us. And also it's a pleasure to make connections, as always in science, I would say. Between different fields. And I know that, of course, sometimes fields are separated that share the same methodologies, though. No? And I decided to give a talk here, which at first looks maybe a little bit long, but we will make it, I assure you. And I will talk in the beginning a little bit about the history of my own thinking, and you will see that at several points, sort of the same mathematical structure as in imprecise probabilities appears, no? For different reasons maybe, but they share the same logic. And then in the second part of the talk, I will introduce a new model that relates somehow model uncertainty and statistics, the so-called smooth model, which is not a very good name, but you know, as it goes, sometimes they don't have the best names in the fields, no? But anyway, and then in the third part, I'm going to present a recent paper about risk and uncertainty sharing. And feel free, let's say, if you think, I'm not sure how much you know about economics, so I will try to explain what's going on. Yeah? The big new idea here being that this idea of trading model uncertainty, yeah? And that this can improve things for the economy. Okay, but let us get started. So 100 years ago, or a little bit more now, Frank Knight published his dissertation, Risk, Uncertainty, and Profit. And 2 years ago, I was invited to a very nice conference, which is also available on YouTube in London, where Frank Knight and John Keynes' books were celebrated. So if you want to have some information, you can still find the videos online. And I took this invitation as an incentive here to read the book by this person here, Frank Knight, who introduced, at least that's how the economists view it, yeah, this distinction of risk and uncertainty that we have today. So it's a little bit a strange title, no? So risk, uncertainty, and profit. No, risk and uncertainty, of course, belong together, but why profit? Well, that's a classic question in economics, maybe a little bit of an academic nature, because everybody knows that profit is around. No, there's Elon Musk, people like that, who make a lot of profit in the real world, of course. However, in a, let's say, theoretical economic model, profit should be zero, no? Even in capitalistic markets. Yeah? So without uncertainty, so definitely in deterministic models, profits are zero in competitive markets. And here you see always in the Chicago green, yeah, I call it, you see a quote from Frank Knight's book. He doesn't use formulas, but in my opinion, he's a mathematician, yeah, because he writes in a very clear way. So in ideal exchange, the quantities exchanged are equal in value terms, which is like a first order condition, let's say, yeah. And there's no chance for anything like profit to arise. That's correct. So Knight claims, and that's the interesting part now, maybe, often in economics, students are taught that under risk is different because the entrepreneur is willing to take the risks. Therefore, he makes money. Huh? But Knight claims that this is not true under risk. That is, in an environment where you know all probabilities, the costs are again known quantities, and then there's no real uncertainty and profits are zero again. And the whole story is proper uncertainty, no? Whatever that is. He is very vague in his book. So one has to admit that's the source of profit. So in this famous chapter 7, yeah, so Frank Knight's book, by the way, is chapter 1 to 6. This is more like the first textbook on mathematical economics without any formula, yeah, but it's like that really. Chapter 7, he studies profit and uncertainty. So let's see how it works. He says, he takes the very nice example of champagne production. So I understand that this seminar virtually takes somewhere place, maybe in northern France, one could say, or in Belgium, I learned. So the champagne is not so far away, no? So, of course, in champagne production, you have a risk, namely that you see by turning around the bottles all the time, sometimes they burst. No? And so that's a cost for you. And of course, it's impossible to predict which bottle will burst. But you don't care, no? Because you have the law of large numbers. So each single bottle bursts at random. But by the law of large numbers, the total number is known to you, and it's a fixed cost for the firm. And the thing is, markets can perfectly price such randomness, and that's what we also learned much later, no, in finance and insurance. That's true. Yeah, such kind of uncertainty, we can price it perfectly. And then he goes on and said, this mathematical type of probability is practically never met with in business. Never, I wouldn't say, no, because he just gave an example himself, no, that we have this, but okay. But the real source of profit, in his opinion, is different. No? Yeah, and that's unmeasurable uncertainty, as he calls it, or typically in economics and decision theory nowadays, we make this distinction of risk when you have probabilities and uncertainty when you don't. And then his point is, yeah, another quote, the income of an entrepreneur is larger as there is scarcity of self-confidence in society. No? So you need to be very self-confident, of course, to tackle such uncertainty. And there's the power to make effective guarantees to employees. No? The thing is, of course, the entrepreneur gives a constant wage to his workers. So that's like an insurance for the workers. So excess profit is the result of confronting uninsurable uncertainty, in my interpretation. That's often the case. And interesting, in the end today, I hope I get there, yeah, we will try to insure this again. Let's see if that works. Okay, just, yeah, if you want to remember, yeah, maybe you remember this no risk, no fun, no? And, well, you can continue in the spirit of Frank Knight, no uncertainty, no profit. So in that sense, you can also say uncertainty has also its positive parts. All right, big jump now. How did I come to imprecise probabilities? Actually, I was doing a PhD rather in mathematical finance, financial economics, with Hans Vollmer at the time. So finance was a big fashion in the 90s. And risk measures, measuring risk, not by variance, but by something else, was a big topic at that time. For example, value at risk that all the banks used for many, many years, by now was invented by JP Morgan. But the Swiss banks were not so happy with it. So therefore, they contacted some researchers whom I know very well, Riedel, for example, of the ETH, and they asked him, can we make I don't know, how do we measure risk correctly? And I remember that when in the 90s, Riedel came to Humboldt University and gave his talk about this paper, everybody thought a little bit, that's a good thing, that's a good structure. You see, that's a nice mathematical structure that can do a lot of things with. How does it work? Well, okay, in economics, or also in finance, you think of a financial position as X of omega principle. And it's a contract that depends on the state of the world, omega. You can think, for example, of X could be really the full bank or something very concrete, like a digital option. You get $1 if the asset price of Microsoft is above whatever. So, of course, in standard economics and finance, you would immediately write down omega as P. But that's what I thought also always as a student. So actually, I don't know the P. So yeah, there's a jump there. And that's what we want to avoid now. So maybe we don't know the P. Here's the definition. We don't work with the P. We just say a measure of risk measures the risk of X in terms of money. Yeah? So the banks want to have a money scale. What does that mean? Well, money scale means if you add money, you reduce the risk. Yeah? So if you, okay, so that's this sort of famous cash additivity. Because we are talking about risk, we have this a little bit strange sign convention. Yeah? Rho X plus M is rho X minus M. So that's for all M in the real numbers. We want it to be monotone, of course. If X is greater equal Y in every state of the world, then the risk should be smaller. And then this is a standard economic principle. Now we want to encourage diversification. So, and as mathematics, this is simply convexity. So then we have the famous Vollmer sheet or Fritelli-Rosazza-Giannini representation. Not so difficult for people who know convex analysis. No, you apply convex analysis to this object, and essentially you get this nice duality here. So you can write every risk measure as a maximal loss. Yeah, this is here the loss under, as I will speak here, under model Q. But then this here that's a penalty function or something that measures the trust, alpha Q. And actually, originally, historically, it started the other way around. It started with a different assumption, maybe even positive homogeneity, which is another strong assumption, as you know. If you do that, then this alpha function only takes the value 0 and infinity. So you can just say I discard all the models where alpha is equal to infinity, and I get representation in terms of a nonlinear expectation. I take the maximal expected loss over classes of models. So that's, I guess, where automatically somehow imprecise probabilities appear, no? From the structure. Not to motivate, that wasn't really the motivation, but of course, model uncertainty plays a huge role in finance. So I think I said this, so let me be a little bit quick here. That's sort of a pessimistic one. Now I jump to decision theory. Now in economics, of course, people have long been aware of this Knightian distinction, and Ellsberg came up with these experiments that I guess everybody here in this audience knows very well. So there's a risky earn, yeah. So in order to translate Knight's thinking into a concrete model, he devised this experiment. So on the left, you have 50 red balls, 50 black balls. On the right, you don't know. So Ellsberg somehow sees Knightian uncertainty as a lack of information about the structure of the model. And then, of course, people behave differently, no? When they are asked questions about whether they want to bet on the earn. Most people, or many people, no, don't like this uncertainty on the right. Maybe some people like it. No, that's not forbidden, of course. So then when I turned to economics, as a doctoral student mainly, they were always teaching this, and then they said, but yeah, it's true, it's really a problem, but we can't do anything. Nevertheless, we go to expected utility, which was very unsatisfying somehow for me. And then later, of course, luckily, since 20 years or so, we have models for that. So what is the problem? Well, the problem is if you don't know the composition of the earn, you have a set of probability measures, because you don't know the exact probabilities. Now, Savage and Anscombe-Baumann, that would be the classic approach. They would just say, who cares? Yeah, we take a second order problem. So Bayesian approach. And then you see here from this, of course, I can define a bigger probability space, and then this corresponds simply to expected utility again, because everything is linear. Now I define a new probability measure, P bar, which is just the average of all the P's. The so-called predictive probability, this will come again. Okay, but this cannot explain behavior in the Ellsberg model. So people later found a solution to that. And that's the so-called ambiguity-averse approach by Gilboa and Schmeidler. And I like the version by Talon and others more. So in the version that Talon and others have developed, first, there is objective probabilistic information as in the Ellsberg experiment. So you know, yeah, for example, that well, there are 20 red balls minimum, but maybe it can go up to 60 or so. No, that would be the objective information. Then the agent is free to subjectively decide which priors to use, and he takes a worst case approach. That's like a risk measure, no? Coherent risk measure. The risk measures came later, no? But we have the same mathematical structure, except for the sign. And also this was, let me mention here, because he's my co-author in the paper that I present later, here's this nice approach by Gastos, Hayashi, Talon, Bernio. But of course, the first axiomatization goes back, it's a famous Gilboa-Schmeidler representation, one of the most cited, well, if not the most cited papers in the Journal of Mathematical Economics by now. In economics, this was also generalized to, like in the spirit of the convex risk measures, same structure, a penalization approach by Maccaroni, Marinacci, and Rusticchini. But I don't go into detail with that. I just want to mention it and to give an overview of what we have. Okay, so now come to my second part, a new approach, which is somewhat in between this sophisticated max-min approach and the Bayesian approach that I mentioned before. And it's very popular now in economics. I'd be curious to see how much you like it here. But before I do that, I stopped talking about finance and economics for a moment, although it's economics, in my opinion. I'm talking about climate science. Now, climate change, of course, is a huge topic at the moment. No? And took me a while to learn it. But then I discovered a textbook, and the first thing that they explain is that climate is a probability distribution. That makes sense, no? Weather is the instance of climate, so you observe rainfall, pressure, temperature, and so on. That's the state of the world. And climate would be the long-run probability distribution of weather. Now, climate change means the probability distribution changes. And in my opinion, it leads to Knightian uncertainty. Let me explain. Yeah? Of course, many models are deterministic, so they act as if this kind of change were deterministic. But let's have a look, it's not so clear. So actually, before I went to South Africa, where I am now, where it is pretty warm actually, I was in Oslo, so you see I had the biggest climate change myself. And since I gave a talk in Oslo, I found actually the data, it's not for every city, it's not so easy to find out, but in Norway they have good data. So this is really the probability distribution in winter of the temperature in Oslo. And you see the average is sort of negative, something like -2, no? You can say it's normally distributed, but it's also not really true, no? Because you have these outliers here at 10 degrees. So that happens from time to time. No? So it's very hot in Oslo, no? 10 degrees. And this is going to change, no? So we have this kind of distribution, and it's going to move, no? So anything like that. It could also be like that, no? Right? Something like that. So definitely a case of imprecise probabilities or Knightian uncertainty. In Oslo, no, by the way, I found out okay, it's a rich country, so they're doing a good job. They are preparing for that. And I don't know if you can read this, I may have to make it larger here a bit. But you see, they also speak like that. No, this is a political paper or by the Oslo, local Oslo government. Increased probability and then potentially increased probability. You know, you see, this is a probability for having a higher probability, right, or something like that, and so on. No? And they try to argue about that, and also some things remain uncertain. For example, strong wind. I don't know if they're very afraid of strong wind, but apparently that seems to be an issue. Okay, coming closer to economics, here's a recent paper by one of the leading figures in the field. It's a paper that is going to appear in the top journal Management Science this year, Michael Barnett, Climate Change and Uncertainty, an Asset Pricing Perspective. And I think he is right that the methods that have been developed in our field are very useful also for this topic here. If you look at the paper, okay, so here, this picture, first picture, so I think everybody agrees that it's getting warmer, although in a very stochastic way, maybe these blue lines. Yeah? And if you look at other things in the paper, for example, here, let me just take this. So that's what is going to happen with profit, let's say, or with wealth. Yeah? So here we have wealth of the society, and here we have the years. And well, it looks quite uncertain. No? They try to make probability guesses. By the way, it could also be that we get much richer, apparently. It's apparently not excluded in these scenarios that they have. But anyway, of course, they expect it to have a harmful impact. But I think we all agree that there is also some uncertainty that needs to be assessed and discussed. How would you model that? Okay, if you just take a statistical model, you would say, okay, here, my reference distribution is what I have from the data. So maybe I estimated minus 2.3 seems to be correct for, I don't know, yeah, for the variance. But let's take that normal distribution, and maybe now we think that it's going to change. So theta is going to be uncertain, the average. Yeah? And for simplicity, variance stays the same, which is not correct, of course. But I don't have too much time now to go into all these details. And then from an economic point of view, first of all, we need to decide how to measure the outcome of various policies. Right? And it's a very crucial question, of course, for this field, and a very fundamental question. There's a lot of debate about that. Yeah, of course, let's say if you look at the literature, they take expected utility, or if you like, what I call the predictive probability before. You see that as before, you have seen this already, x of omega. Now it would be the outcome of the policy, GDP in 30 years, or whatever, the health, no? And then you measure welfare at the risk with a certain Bernoulli utility function. And Savage and Anscombe-Aumann would just take expected utility under the predictive probability measure. So here I have a parametric model, and as usual in statistics, I can take the average over all parameters theta. So here my friends Klibanov, Marinacci, and Mukherjee, they developed a new model that is sort of in between the models that I presented before. You see, the Gilboa-Schmeidler model is very pessimistic, maybe too extremely pessimistic. So they try to find something in between, which is in the spirit of the Bayesian approach. Here we have, of course, two layers of uncertainty. We have x of omega, and we have the parameter theta. And both x of omega, you can say, if I know theta, this is risk. And this here would be the parameter uncertainty. This is uncertainty. So if the climate is known, I know I have only risk. Otherwise, I have uncertainty. So we can view it as this is very standard also in statistics, of course, as you know, as a second order uncertainty. It's another random variable on a higher level. How can we do this? Well, if I fix, if I fix theta, so then I can compute what is known as the certainty equivalent. So u of c is equal to expectation under theta u of x. So it's the amount of money that makes me indifferent between having the risk x and having the amount of money c. Typically that is smaller than the expected payoff. But now I can view this object as a second order risk. Well, I will call it uncertainty, of course. The theta is also unknown. So, but let's do expected utility there again. That's the idea of the smooth model. So I introduce, and I don't like this uncertainty, I introduce a concave utility function v, another one. And we'll simply take, and then also need a prior mu. And you see here, this is expected utility, but it's a second layer, So sometimes I will speak of v and u, because these are the two, economically, these are the two fundamental functions. But of course, I can also write in the following form that you will see this sometimes. If I define a new function phi, which is v of u minus 1, then I can write the total utility as the expectation under the second order prior mu of phi of expectation under the risk, theta u of x. And phi is the mu part. So if phi is the identity, I'm back to the expected utility model. And if phi is very ambiguity averse, so if this object here, minus phi double prime phi prime, measures the aversion to ambiguity, if this goes to infinity, I go to Gilboa-Schmeidler. So I will be very pessimistic and go for the worst case. Okay, didn't see anybody interrupting me, so I assume it's okay. So for example, in a recent paper, which is much more general than what I present today, but with Max Nendel, who was also mentioned here, and Maren Schmeck, which appeared in insurance, we look also at this here a little bit. What would happen for insurance? Well, you see, if something is normally distributed with mean theta and variance sigma square, the fair premium is the expectation. So we take, fair premium is just the expectation. And then typically there's a charge on top of that, You take some number A and then maybe sigma square half, yeah, the variance. That's a classic theory of mathematical insurance. And now we have here two layers. So, typically they would say, okay, take a second order prior, maybe also normally distributed, or the conjugate priors then. And to justify the pricing, we assume that the company has a utility indifference principle. So they're using a utility function of this form, exponential, yeah. And now let's, in the spirit of that, let's assume that the second order utility is also, maybe with a different parameter b, exponential, so has constant ambiguity aversion. And then we can compute the insurance premium. Yeah, that's very simple. You can do this as an exercise at home. Yeah, I just show you what happens. So classically, it's mean plus some premium for the variance. Now we get, if you can call this the average mean, because I average over all the thetas, I get here the first order variance, and here I get the second order variance. This is a common theme in the economics literature, that you get a premium for this uncertainty. I took a too simple example, maybe, no? Keep that in mind. Yeah, don't feel a little bit unhappy with this now, but I just took this very, very simple example to show how one can model these things. Recently, there's been a new approach in economics that relates this kind of uncertainty with statistics. In statistics, we have this important concept of identifiability. So, okay, so sorry, it's a typo. No? A statistical model omega f and a class of probability measures p theta, theta and theta is identifiable if there exists a function k from the states of the world into the parameters that identifies theta, no? Which means k is equal to theta, p theta almost sure. If you know that, perfect. If you don't, I just give you quickly two examples. IID models, no? These are examples where you can learn the parameter perfectly. So I'm moving down a little bit really from complete uncertainty, to things where we can learn parameters. So simplest example, I have infinitely many experiments. I don't know the mean of the normal distribution. I can go to the product measure, no? And then by the law of large numbers, this function here identifies the parameter, as you know. Now, okay, very simple. This is actually true for all ergodic models. No? Other model, which is a little bit different, no? But the Ellsberg model is like that. Here you can identify everything because, well, you can identify if ex post you are allowed to verify the error. So that's different. Here you don't need infinitely many experiments. That would work as well, of course. But here's maybe a setting where for some reason you can identify the parameter because you can check for some unknown information. I will give you another example later. And in a very interesting paper just appeared in Econometrica by Denti and Probato, they show that in that case, our utility function can be written like this. Yeah, it's phi of the conditional expected utility given k. Yeah? Because k identifies the model, the risks. So k is somehow measures the uncertainty. No? So sigma of k is the sigma field of pure model uncertainty, I would propose to call it. And then at the second layer, you take again, you use phi for ambiguity aversion, and then you take again the expectation ex ante sort of, yeah. Because in the beginning you don't know the unknown parameter, of course. And because in another paper we have shown that under Knightian uncertainty markets don't work very well. And that was always asking myself where that comes from. And when I saw this, I realized that that's a problem. We don't know the k, yes, somehow. So Knightian uncertainty is lack of second order information. Now, of course, then as a consequence, under identifiability, maybe I'm back to insurance. Some people don't like it. I don't know, my wife told me, but if you make climate change, if you insure against climate change, then people don't panic anymore. It's true, but maybe that's not the worst thing. We can discuss it. So now let me come as in the last minutes to our new paper, where two of the people are involved that I mentioned, yeah, Mukherjee, who invented the smooth model, and also Jean-Marc Talon, who has written about this Gabor-Schmeidler model and ambiguity as lack of information. So the paper is called Efficient Allocations Under Ambiguous Model Uncertainty, has not yet appeared. It is also joint work with Chakihara from Kyoto University in Japan. So now we take the model that I described very lengthily, and take it to economics. Yeah, so a theory is represented by probabilistic forecast, just a bit different language, but it's just a P, probability model that corresponds really, in our case, to a physical model, maybe a model of climate. So each model is based on certain parameter values being true. And you can identify it ex post. Now, I understand that climate change, if you can identify it after 30 years, but then it's questionable, but take it as a benchmark model. No, and nevertheless, of course, in 2050, we will be able to say to some extent, climate has changed by at least 1 degree or 2. I think such things can be settled. Yeah, so okay, I skipped this a little bit. There's a young farmer. Climate change, uncertainty, of course, is very dynamic, and it appears in other fields, leading to the fact that some people disappear quickly, like this guy here in the middle. Here's the same thing. We understand Birros dynamics very well, but in the beginning, there's a lot of uncertainty about the parameters. After a couple of years, maybe you are able to identify the parameters. Finance, the field where I originally come from, has also models. And there you see, I mentioned this paper here that I've written with Patrick Beisner, who's now in Canberra in Australia. There you have models where the volatility of the asset is not known, so the sigma here. And because it's in continuous time, this model is really identifiable perfectly because the quadratic variation is observable ex post. So here we really have a fully identifiable model. And in our paper in Finance and Stochastics, we have shown that the market breaks down under some circumstances. It's not nice, of course. So maybe what I present now, it's not in continuous time. We still have to work on that. It might be a solution to that problem. But actually what I'm going to do in the first place, and I'm not sure if you know that literature, I'm just doing risk sharing, actually uncertainty sharing. So it's very simple. Yeah, it's much simpler than markets. I don't do markets today. It's just risk sharing. Easiest example, there's Adam and there's Eve, yeah? And if Adam has 1, Eve has 0. And if Adam has 0, Eve has 1. Now that's a nice society, because if they don't like the uncertainty, yeah, if I take this, the sum is always 1. No? So how can they get rid of the uncertainty? They just share it. No? They say, Adam says, if I have 0, you give me 1/2, okay? But then other way around as well. And then they agree on that. Actually, the solution is only 1/2, by the way, if they have equal risk aversion. You will see that. But okay, but that would be a typical fair solution. Example 1 is health insurance, where actually it's the same idea. Some people get very severe diseases, But if we think that these diseases are ex ante IID, then from the point of view of the insurance company, every year, certain fixed number of people get the disease, we can compute the total cost, we share it. And last example, less clear, maybe production under climate change. Also there, countries, companies also could share the risk. But it's not so easy also to do, particularly in the case of climate change, as we know. Talking to 180 countries or so, and get a solution is not easy. So here, for the first moment, all we want to understand is what is actually good here in such a situation. So we analyze how optimal allocations look like. We do not yet ask if markets can do that. Sometimes it's easier if markets can do that. Oh, I have a question that I missed probably long ago. Okay, I come back to that. Sorry, I didn't see it. I explained it at the end. So this is another question. Yeah, so maybe markets can do that. That would be nice because then you don't need government contracts and so on. But maybe it's needed nevertheless. No. First of all, we want to understand how that works. In order to, since I was not sure if you know the literature on that particular issue, let me first do what is known. If there's only risks, so Adam and Eve know the probabilities. They have some Bernoulli utility function, and the average risk is x, and everybody has x1 and x2. Yeah? So what you do in that case, you maximize the sum of expected utilities. It's called the welfare of the society, subject to the constraint that you sort of redistribute the risks, what I did before with the 1/2, 1/2. Now this is very simple because this max expectation P U1 Y1 plus U2 Y2 under the constraint is max expectation P U1 Y1 plus U2 aggregate risk X minus Y1. And then one can show that I can simply take the max into this expectation. So it becomes a linear thing and a real value, not a real valued thing, U1Y plus U2. Yeah, I write explicitly X omega minus Y. So first order condition is the two marginal utilities, as they say, must be equal. And then you can develop a full theory from there. For example, if X of omega is always 1, then Y is deterministic. No? And you get what is known in economics as full insurance. Full insurance is optimal. You see, if the functions are the same, then it's actually 1/2. But if they're not the same, it might be different because typically the person who is more risk averse is willing to pay more for the insurance, and then there's a slight shift in the sharing. So that's what I said. Yeah, Adam and Eve share preferences 1/2, no, otherwise not. For example, if I have UI y is equal to minus exponential minus AIX, that's a case that I consider later. Then I get Y1 is depends on the sum of risk aversions and the value of the other person. So it's linear, yeah? Linear risk sharing. And the person who is less risk averse gets more. Yeah? So if alpha 2 is bigger than alpha 1, then I get more. Okay, that was the review. Other thing that you can derive here from this equation star, you can show by implicit differentiation that Y1 is a monotone function of X, and then by symmetry Y2 as well. So they are so-called comonotone. Yeah? So if society grows, everybody gets more, for example. Okay. This is old, yeah. You see, Wilson characterized all utility functions that have linear risk sharing, but oh my, I'm very slow today. Sorry for that. So I skipped that. Let me know if you want me to stop. No, I don't know. It's 45 now. Maybe you can just write it in the chat how much time I have. Okay, good. Then let me say what I want to do. In principle, I want to do this risk sharing now under uncertainty. In the paper, of course, we do finitely many agents, but maybe it's fine for the talk if you think of 2. They have these Bernoulli utility functions, and they have these phi I, so which is Vi of Ui minus 1. So Ui now can answer Jasper's question, measures risk attitude. And in my opinion, yeah, but there's a debate. They cannot decide in the literature yet. I think VI measures second order uncertainty attitude. However, the people who have invented the smooth model say, no, it's phi I. So it's not VI. Yeah? But that's a philosophical discussion. But you see, so I think because the utility in the end is expectation under some predictive probability of, let me write it like this, sorry. Let me write in the traditional way, so like this, expectation of second order prior, VI of certainty equivalent, yeah, which depends on UI, of X. So you see, then VI is really like risk aversion, but for theta. So that's why we would like second order uncertainty attitude. So now here's the new idea of the paper. Model contingent consumption. So since we assume that ex post, so after 30 years or so, uncertainty is identifiable, we can write contracts on the models. Yeah, for example, you get €1 million if the temperature has risen by 2 degrees in 2050. This is a little bit like weather derivatives that have been invented long ago. They're not so comfortable, they're not so traded, they're not so fashionable. So I would need to go maybe to climate insurance, no, instead of weather derivatives. But the idea is very similar. In my model in finance that I presented before, we have such things already in the markets, options on volatility to some extent. It's always only an approximation. So the new thing in our paper is that a consumption plan now depends on the model, and we can justify this by saying, yeah, ex post, we can identify the model. So that model has not, as far as I know, been studied before in economics, and therefore we can do that now, and have a look what happens. Yeah, so it's a little bit different because now consumption doesn't only depend on omega, but also on k of omega. So it gives me more freedom to determine my consumption. I think I can skip this. In principle, let me go directly to the mathematical problem that I want to do. We do as before, lambda you can take equal to 1, yeah. But of course, it's okay if we vary the lambdas, they can reflect different power in a society or wealth or so, yeah. But for the talk, we can take lambda equal to 1. We just maximize the sum of utilities subject to the feasibility constraint. We just redistribute all the excess by writing some contracts. The resulting function plays an important role in economics because it's called the representative agent. It sort of summarizes the society, in one function. And of course, you hope that the V has a similar structure as the UIs. And indeed, normally for the smooth model, it's not true. But here we will see it's a little bit true. So let's see. First of all, before I start, I record the results that we know from risk sharing, yeah, under risk. The set of efficient allocations is independent of P because you remember max, EP, blah, 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 was EP max. So actually the solution doesn't depend on P. It's nice, it just depends on the aggregate endowment. Lambda was 1 in my example, so you just have to set the marginal utilities equal, and the allocation was co-monotone. In particular, we get full insurance in the case of no aggregate uncertainty. So now I look at this model here. I maximize over all feasible allocations, the sum of utilities. And here, as before, the max goes into the integral, but the second integral. But that helps a lot, of course. So my solution is going to be independent of the second order prior. And then I have a sum of lambda I, phi I of the expected utilities. So there's a non-linearity here. So I can't take the max again into this. No? Nevertheless, phi I is strictly increasing, of course, as a utility function. So it's a monotone transformation of this. And you know, in optimization, if you take a monotone transformation, we still get sort of the same solution, but maybe for different weights. So what we learn from that in this model, but it's really crucial that I can condition on P, you get the same efficient allocations as in the classic risk case, which is very nice. Yes, because then we know what good allocations are. So we know where we're going to go. Yeah. From that, we learn that if XIP is an efficient allocation ex ante, then it's also co-monotone, like in the classic case. Get the same class of allocations. They don't depend on the P's and Q's, so the whole set of allocations. Yeah. And if the area endowment was unambiguous, which is not, yeah, because okay, if there is no climate change, then we don't need the theory, maybe, yeah. But also, okay, but nevertheless, in cases where everything is unambiguous or not uncertain, so certain, yeah, deterministic, let's say, then also what you get is deterministic. How does the first order condition look like? It looks a little bit like before, but you see, before there was only this term. And now there's a new term, this here. And this is uncertainty adjustment. Yeah? The marginal utility of the uncertainty. So this, in the end, you get a very nice theorem. The representative agent is of this form. So you have, again, sort of smooth model because you take an average, but it depends on P. So it's like state-dependent expected utility, yeah, but at the second level. I'm really late, so because, and then I think at least I want to show you in the case of constant risk tolerance. So everything is like exponential functions. I want to show you what happens. You remember in the beginning, Adam and Eve were sharing in a linear way with their allocation. Now they do something new. They do uncertainty insurance, which is just cash in this case. So there's a number, tau IP, that goes from one person to the other that they exchange. And now I just show you the picture. This is profit here, but let me explain what's happening here. So first of all, here on the x-axis, you see wealth. Yeah, this is actually the certainty equivalent of society under some model P. So let's and we see ex post, we know what. Yeah. So if here the society is rich, yeah, so climate change was not so important, and here the society is poor. And what's happening is, this is an insurer, yeah. So he is very poor. He loses a lot of money if climate change is really heavy, and then the farmer gets a lot of money. And the other way around, if farming is perfect, no problem with climate change, then there's excessive profit in the sense of Frank Knight. So coming back to my beginning, yeah, that's where the profit emerges, maybe due to uncertainty. Okay, in the paper, actually, we do a little bit more, but I thought that this is a little bit too much to discuss. If you like, you can have a look. At this also, we have an application to macroeconomics, which I can go over if you are very interested. But since I think time is really coming up, I would like to summarize here. So we have seen that Knightian uncertainty, as it's called in economics, is a new paradigm, in my opinion. Yeah, it has a lot of applications in various fields. I explained the smooth model that provides a link between decision theory and statistics, and I showed that, what the implications are for economics in the very first preliminary step, where we look only at risk and uncertainty sharing. If you want to find more, here's my webpage, and I thank you very much for your attention.